Hey, boppity beepo, boppity boopa. Let's start chapter 2. Let's talk about some relations and functions. Okay, a relation is just a set of pairs of inputs and outputs. So there's four ways you can kind of show a relation. You can just show the ordered pairs. Here's the relation, -3 goes to 4, 3 goes to -1, 4 goes to -1, 4 goes to 3. That's a relation. We're relating some inputs to some outputs. You can draw a mapping diagram. Okay, we're showing the same relation here. -3 went to 4. Here, -3 goes to 4. 3 goes to -1, just like it did here. 4 also goes to -1. 4 also goes to 3. So there's a map showing the pairings of these inputs and outputs. Table of values is another way, which is very similar to this, except it's a table, right? Still showing which input is related to what output. And you can show it through a graph. So a graph is showing -3, 4. Here's the input, the x input -3 being associated with the y output -4. Here is the x input 3 being associated with the y output of -1, and so forth. So let's pretend we're skydiving. I have no idea why anyone would jump out of a perfectly functional airplane, but hey, for some people it's fun. I don't know, I think I'd just prefer to like maybe drive a little too fast or something if I needed a thrill. Anywho, these pictures show the person's distance from the ground, the person's elevation, a certain numbers of seconds after they jump out of the airplane, like a weirdo. So at 0 seconds, they're in the airplane at 10,000 feet. After 4 seconds, they're 9,744 feet off the ground, which makes me terrified. After 8 seconds, they're 8,976 feet. 12 seconds, this many feet. 16 seconds, that many. Uh-oh, you're getting closer to the ground, dude. I'd be worried right now. Okay, so how can we represent this relation in 4 different ways? Well, here's one. We can make a mapping diagram. We can consider the height, or we can consider the time after jump to be our input, and then our output would be their elevation. So at 0 seconds, their elevation is 10,000 feet. At 4 seconds, 9,744 feet, and so on. We can also represent that as ordered pairs. Remember the curly brackets say this is I'm beginning a set, and here are the points in my set. 0, 10,000, 4, 9,744, and so on. I can make a table of values. When time is 0, height is 10,000. When time is 4 seconds later, 9,744, and so on. Or I can draw a graph. When time was 0, we were at 10,000 feet. When time was 4, we were at 9,700-ish feet. Time was 8, we were at 8,900 so on feet. And then these dots show us the height after the given time has elapsed. So there are 4 ways to represent that relation. Okay, so here we have a problem. You can pause and try to do this on your own, and then push play when you're ready to see me go over it with you. Alright, so the monthly average water temperature in the Gulf of Mexico in Key West, Florida varies during the year. In January, the average water temperature is 69 degrees. In February, 70 degrees. In March, 75 degrees. In April, 78 degrees. Let's see, how can I represent that as a relation in 4 different ways? Well, if I number the months and I call January month 1, let's see, month, I guess I'll start with a table. And then temperature. In month 1, the average water temperature was 69 degrees. In month 2, it was 70 degrees. In month 3, it was 75 degrees. And in month 4, it was 78 degrees. I could also represent it as a set of ordered pairs. 169, 2 comma 70, 3 comma 75, and 478. Let's see. I could also do a mapping diagram. My months over here. And my temperatures over here. My temperatures were 69, 70, 75, and 78. And this one's easy. I just draw an arrow from each input to the output it corresponds to. And then last of all, I can make a graph. So I'll make the horizontal axis my months, and my vertical axis my temperatures. And then at 1 month, my temperature was 69 degrees. At 2 months, my temperature was 7 degrees. In the 3rd month, I was 75 degrees. And in the 4th month, I was 78 degrees. So there are 4 ways to present this relationship, this relation, if you will. So now we're going to talk about these terms domain and range. So the domain of a relation is the set of all the inputs. We think of those as the x-coordinates or the inputs. The range is the set of all the outputs or y-coordinates. So let's use the relation from problem 1 and find out what the domain and the range are. The domain is the set of all the inputs, your x values. So it's going to be the set including 0, 4, 8, 12, and 16. There it is. The range is going to be the set of all the outputs. So 10,000, 9,744, so on and so on in blue. So the range is the set of the y-coordinates. Alright, so what are the domain and range of this relation? Alright, the domain is the set of all the x-coordinates. And we generally try to put them in order from least to greatest. So I got -3, 0, 2, 9, and 23. Well, nicely enough, those are already in order from least to greatest. -3, 0, 2, 9, 23. That is my domain. Those are the only numbers that are inputs in this relation. What about my range? Well, my range is the set of all my outputs, or all my y values. So I've got 14, 7, 0, -18, and -99. So my least output value is -99. Then I've got a -18. Then I've got a 0, a 7, and a 14. Now one thing that you should know is, what if I have the same input showing up multiple times, or what if I have the same output showing up multiple times? So here's another sample. So what would be the domain of this set, or from the domain of this relation? Well, I've got 2, I've got 2 again, got 3, and I've got 4. I only have to say the 2 once, so I don't have to state it twice as being a member of this set, called the domain. So 2, 3, and 4 would be the domain. And the range, I would have a 3, a 4, a 3, and another 4. So the only unique numbers that show up in my range are 3 and 4. Domain and range. Also pumpernickel, because pumpernickel is the secret code word / code phrase for this lesson, pumpernickel. So we're going to talk about now something called a function. What's a function? A function is a special type of relation where each element of the domain corresponds to only one element of the range. So when you're trying to identify a function, what you're really looking for is, you're going to say, all right, it's probably a function unless I see one thing in the domain mapping to two different things in the range. So when you're trying to tell if a relation is a function or not, you're basically just looking to see if it's breaking that rule or not. If it's breaking that rule, it's not a function. If it's not breaking that rule, it is a function. All right, let's do a couple examples. So my domain has -3, 0, and 4. -3 goes to -2, 0 goes to 7, and 4 goes to 1. So what I'm looking for is, does it break this rule of each input going to only one output? No, it's not breaking that rule. -3 only goes to one place, 0 only goes to one place, and 4 only goes to one place. So that's a function. What about on B? 4 goes to -1, 8 goes to 6, 1 goes to -1, 6 goes to 6, and 4 goes to 1. Does this break the rule? The answer is yes, it breaks the rule, because right here we've got 4 going to -1, and right here we've got 4 going to 1. So one single member, one input, 4, is getting mapped to two different outputs. So that is not a function. Alright, so try number 3 here, A and B, and see if you can tell if it's just a relation or if it's a function. Push play when you're ready to see. Alright, did you notice that this input 2 is being mapped to two different outputs? -3 and 3. That breaks our rule, so it's not a function, it's just a relation. What about on B? What are my inputs? My inputs are -7, 9, 14, and 7. I've got 4 different inputs, so I don't even have the possibility of it saying that one input is going to two different outputs. -7 only goes to 14, 9 only goes to -7, 14 only goes to 7, 7 only goes to 14. I don't have one input being mapped to two different outputs. So yes, this is a function. So remember, x's were our inputs. So if this is think about this. What does it mean for one input to have two outputs on a graph? So my one input here, whatever this value is, if it has two outputs, it's going to have 2 points touching in this one vertical line. So if a vertical line touches a graph twice, if any single vertical line touches the graph twice, it's not a function, because that gives you one input, one x value, that's being mapped to two different outputs, two different y values. So that's where we get this thing called the vertical line test. You can take a graph and just imagine a vertical line at every single point along the graph, and if one single vertical line ever touches the graph in 2 spots, it's not a function. Alright, so let's take a look at these. A, is this a function? No, because this vertical line is touching the graph in 2 places. Is this one a function? Yes, anywhere you draw a vertical line, that vertical line is only touching the graph in one spot. And then on C, you've got 2 points right here with the same x value. So there's one input giving you 2 different outputs. Not cool. So this A is not a function, C is not a function, B is a function. Alright, why don't you pause and see if you can tell which of these is a function. Alright, A, what did you say? I hope you said it's not a function. because I can draw a vertical line that hits two places on the graph. So that means I have one input being mapped to two different outputs. Not cool. What about on B? If I look at each one of these points and imagine a vertical line going through each point, it's not touching any other points. Another way to look at it is if I was to pass this vertical line across the graph, 1, 1, 1, 1, 1, 1, it's only ever touching one point at a time. So this one's a function. What about C? If I was to pass a vertical line along this graph, it's only ever touching in one spot at a time. So that's a function. So what's a function rule? And what is function notation? A function rule is an equation that gives you an output depending on whatever the input is. So y equals 3x plus 2 is a function rule that says the output is 3 times the input plus 2. Function notation is a special way of writing a function rule, and the output is called f of x, meaning the output is some function of our input x. So this is just another way of writing the same function rule here. But instead of calling our output y, we can call our output f of x. It's some function of the input x. But this is the same rule if you read it. It says f of x is 3 times the input plus 2. This doesn't mean f times x. This is a special notation that means a function in terms of the input x. So say we wanted to look at a specific input. We would say f of 1 is 3 times 1 plus 2. And then when we simplify, we would say f of 1 equals, let's see, 3 times 1 is 3 plus 2. F of 1 is 5. And we would never do this, multiply f times 1 and just say f equals 5. We keep it this special notation that says this function evaluated for the input 1 is 5. So the output is 5 when the input is 1. The independent variable is the input, and the dependent variable is the output. Okay? The reason we call it the dependent variable is because its value depends on whatever the input was. Alright, so the dependent variable, because its value depends on the input value. Alright, so using function notation, let's look at problem 5. For f of x equals negative 2x plus 5, what is the output for the inputs negative 3, 0, and 1/4? Alright, so when our input is negative 3, we plug a 3 in for x. So we say f of negative 3 is negative 2 times our input negative 3 plus 5. So our output, f of negative 3, is 11. So this is f of negative 3 is 11. What about 0? F of 0 is negative 2 times 0 plus 5, and that's going to be 0 plus 5. So f of 0 is 5. When our input is 1/4, we're going to put a 1/4 in for x. F of 1/4 is negative 2 times 1/4 plus 5. Negative 2 times 1/4 is negative 1/2. Negative 1/2 plus 5 is 4.5. So f of 1/4 is 4.5. Alright, go ahead and pause and see if you can figure out these problems using function notation. Push play when you're ready to see them. Alright, here we go. For A, if x is negative 2, f of negative 2 is negative 4 times our input, negative 2, plus 1. So f of negative 2 is negative 4 times negative 2 is 8, positive 8. So that means that f of negative 2 equals 9. All right, B, we're going to do f of 0. So that's going to be negative 4 times the input 0 plus 1. F of 0 equals negative 4 times 0 is 0. So f of 0 equals 1. And for C, we're going to do f of 5. So that's going to be negative 4 times our input 5 plus 1. F of 5 equals negative 4 times 5 is negative 20 plus 1. So f of 5 equals negative 19. So we can write function rules to model real-life situations. How about tickets? Tickets to a concert are available online for $35 each, plus a handling fee of $2.50. And that's always so annoying, right? You have to pay an extra fee to buy tickets online. I'm going to vent for a minute. I never buy my movie tickets online because I have to pay like an extra $2 just so that some guy at the ticket counter doesn't have to do his job. That doesn't make sense to me. Anyway, $35 each ticket plus a handling fee of $2.50. The total cost is a function of the number of tickets bought. What function rule models the cost of the concert tickets? So there's one question. What function rule models the cost of the concert tickets? And then a second question is evaluate the function for 4 tickets. So we're going to find out the cost for 4 tickets. Alright, well, we need to relate. The total cost is the cost per ticket times the number of tickets plus that ridiculous handling fee. So let's define some variables. Let's let t equal the number of tickets. So then let's call c of t be the cost as a function of the number of tickets. So then what would our function be? Our cost as a function of the number of tickets is $35 times the number of tickets plus the ridiculous $2.50 handling fee. So our function notation is thus: c of t, the cost depending on the number of tickets, equals 35t plus 250. So then let's evaluate for 4 tickets. The cost for 4 tickets is 35 times 4 plus 250, which is $142.50. So the cost of 4 tickets is $142.50. It must be good. It must be a good concert, because that's expensive. I only paid like $35 to go see Imagine Dragons, so better be a good concert. Alright, pause, see if you can do number 6, and then push play when you're ready to see it performed by your math teacher. Okay, I'm buying sports drinks for a softball team. Each bottle costs $1.19. So if I'm going to relate, I'm going to say that the total cost is the cost of one bottle times the number of bottles that I get. So let's say I'll let D be the number of drinks. I picked D instead of B because sometimes my B looks like a 6. So I'm just going to pick D for drinks because that doesn't look like a 6. And then I'll do let C of D equal the total cost. So then my function is going to be C of D, the cost depending on the number of drinks, equals the cost of a bottle times the number of bottles of drink. So 1.19 times D. Alright, now I need to evaluate the function for 15 bottles. C of 15 is 119 times 15. 1.19 times 15 is 1785. So C of 15 equals 1785. That means I'm going to drop $17.85 on sports drink. Alright, now you can work on your practice problems and then go straight to your formal write-up. Make sure you email me if you have any questions. Talk to you later. Bye.